Hello everyone, welcome to the presentation for the paper entitled Decentralized, Covert and Collaborative Radio Surveillance on a Group of Mobile Ground Nodes by a UV Swarm. My name is Helong. I'm from the University of New South Wales, Sydney, Australia. Today's presentation consists of the following 5 parts: introduction, problem statement, proposed solution, simulation result, and conclusion. Now, let me start from introduction. UAVs usually have high probability of line of sight with other objects. This property and their mobility make UAVs widely applied in wireless communication support, radio surveillance, monitoring, and target tracking. We now explain several terms that's important in this paper. The first one is radio surveillance. We also call it eavesdropping. It means that a team of UAVs is used to collect the wireless signals transmitted between a group of mobile targets. And for the purpose of knowing what the targets send to each other, the UAVs should be able to decode the collected signals. Another important term is covertness. So it means that the UAVs should behave in a way such that the targets do not notice that they are under surveillance. In other words, the UAVs carry out video surveillance on a set of targets, but they do not wish to be noticed by the targets. There are several key issues we will address in this presentation. The first one is how to characterize covertness. The second one is how to simultaneously account for the disguising purpose and the objective of eavesdropping. The last one is how to design trajectories for the UAVs in the decentralized manner. To address these issues, we need to formulate our problem, and to do that, we need to introduce some basic system models. Let's start from the UAV dynamic model. The UAVs are modeled by this non-holonomic dynamic model, and we have control inputs UVW representing the linear speed, angular speed, and the vertical speed. All these control inputs are bounded by some certain values. We have a set of ground nodes, ground targets, and their locations are represented by Q. The locations of these targets are measurable by the onboard sensors on the UAV, and the UAV can make a short-term prediction about the target's locations. The distance between a target and a UAV at time t is denoted by DIGT. The UAVs and the targets are assumed to have line of sight. The ground-to-air channel has a large scale and small scale fading. The SNR at a UAV for a target at time t is denoted by SNR IJT. Here, Yij is a random variable which follows the non-central chi-square distribution. The collaborative eavesdropping performance is actually the summation of all the SNRs of the UAVs on a target at time t, and it is represented by FJT. To ensure the successful decoding of the collected signals, we require that the collaborative eavesdropping performance FJT should be no smaller than a given constant C for any target at any time. Okay. Since there are more than one UAVs flying in the sky, we need to make sure that they can avoid the collision with each other. To ensure that, we require that at any time, the distance between any pair of UAVs is no smaller than a given constant, 0. We also require that the average distance between a UAV and the targets satisfy this constraint. It means that the average distance is no smaller than the given constant di. Di depends on the size of UAV I. And in practice, the larger the UAV, the higher the value of di, and it means that the larger the UV, the more noticeable this UV is. Then we need to select a large value for d, so this distance can keep a large distance from the target. For the model of disguising, our idea is that to hide the intention, the UAVs should not monitor a target at a relative distance and a relative angle. So with this idea in mind, we propose to use the derivatives of the UAV target distance and angle to model the disguising performance. And the rationale is that the larger the derivatives mean the more significant change occurs between the UAV and the target. So for the disguising performance, we use the linear combination of the derivative of the angle and the derivative of the distance. Now we have enough models to formulate the starlight optimization problem. This problem is to maximize the overall disguising performance. And we can see here that there is a weighting parameter, di. So here it means that a larger UAV should make more effort in disguising. We also consider several practical constraints. So the first one is the overall collaborative eavesdropping. Okay. The second one is the collision avoidance, and the last one requires the average distance between a UAV and a target. This problem is not easy to be addressed because the objective functions have some terms that are non-convex with respect to the variables, and they are the derivative of the angle and the derivative of the distance. So to address this problem, our solution is to discretize the system first. So we discretized the control signals. The control inputs are selected from the given range, and we just select a finite number of feasible control inputs. Based on this class of control inputs, we developed model predictive control based trajectory optimization scheme. It has the following main procedures. Firstly, we estimate. This scheme is implemented on each UAV separately. So for any UAV, it estimates the positions and the headings of the other UAVs. It also estimates the positions and the speeds of the ground nodes. Moreover, it makes some predictions on the locations of the nodes and the nodes for the coming L slots. So L slot is the horizon. And next, it considers all the possible control inputs from the class that we mentioned in the last slide. Okay, it do a exhaustive search in this feasible control input. Then from the feasible solutions, we select the set of control sequences that delivers the maximum in the objective function, satisfies all the constraints. Lastly, we implement the first step of the control input of the control sequence and discards the others of the sequence. So these steps will be repeated during the mission duration at each UAV. Robust version. In practice, any estimation and the prediction methods may occur some errors. Okay, so it is necessary to take these errors into account in the trajectory design phase. So to do that, in this paper, we assume that any predictions or estimations are bounded. Okay, the errors are bounded. Then we make some extension to the original constraints, and they are represented here. The constraints are actually narrows the solution space, and the proposed method can still be used here. We now apply the proposed method in some simulated scenarios. So we consider three methods. The first one is the initial solution, okay, not the robust one. The second one is the robust version. The third one is a purely random method. So we have 8 figures here. The first two shows the trajectory by the initial method, and the second two are the results of the robust version. The next two are the trajectories generated by the purely random method. The last two figures compare some metrics during this period of time. So we can see that in figure G, we compare the signal to noise ratio. We can clearly see that the red curve and the green curve all have some parts below the constant C. Okay, but for the blue curve, all its parts is above this threshold. And on the right hand side, on figure H, we can see that the cumulative objective values of the three methods are somehow similar. Next, we considered another simulated scenario. We have 3 ground nodes here, and they are moving along a trajectory, and we have 2 UVs carry out the radio surveillance. The figures represent the same thing with the last slide, and we can observe similar results. In figure G, we have some parts of the red and the green curve below the constant C, and in figure G, we can see that the cumulative objective values are somehow very close. So we can draw the conclusion here. The proposed method, especially the robust version, can achieve a good performance in disguising without sacrificing the disguising purpose. Here we make the conclusion. In this paper, we consider a scenario where a UV swarm is used to collaboratively and secretly eavesdrop on a set of mobile ground nodes. We propose a new metric to describe disguising performance. An optimization problem is formulated with the objective to maximize the disguising performance subject to uninterrupted radio surveillance, collision avoidance, and aeronautic maneuverability. Decentralized MPC-based method is developed, and this method can be implemented separately at each UV. We also extend this method to the robust version, and it is tolerant to some inaccurate estimations and predictions of the UVs and the ground nodes positions. This is the end of the presentation. Thank you.